Hello CIO world, and welcome to another installment of chemical engineering. This is control valves. The use of a control valve is of course to control flow rates, but it is also indirectly used to control things like pressures, temperatures, etc. It obviously goes hand in hand with a control philosophy, what have you. So if you want to control um, composition, reaction rates, etc. Control valves are usually going to manipulate the manipulated variables, obviously, which can be directly or indirectly associated to what is being controlled. Now consider placing a control valve in the delivery line of a pump, for instance. Uh, if the control valve is half closed, and you close it further, then the pressure in the line between the pump and the control valve would of course increase accordingly due to the restriction of flow, while the flow out of the control valve would also obviously decrease. So control valves are very useful to make sure that our process control philosophy can be achieved, and in this lecture we will learn how to design them so that they are able to do the control efficiently. The proper installment of a control valve is shown here, where you typically would have two gate valves that are placed on either side of the control valve with a bypass line. Now, can you think of why such a configuration would be desirable in industry? Well, the gate valves are used to obviously ensure that the control valve can be isolated safely when maintenance is required or there are any other issues. And a bypass line is used, usually with a globe valve, to ensure that the process streams can still flow past unhindered so that the process doesn't have to stop. For example, if you need to replace the control valve, take it apart, etc., check the plugs, if it's a double port, or check one of the plugs or whatever, and also check the gaskets that are still intact. If there's issues with the control valve, then obviously you want to be able to get in there safely. When the control valve is in use, it is also very important not to allow the gate valves to be left in any other position other than being fully open. If this is not the case, then the edge of the gate that blocks the flow can be eroded away over time. So it's like holding your hand slightly into a stream of flowing water. Eventually you're going to get some, your skin will start to get soft. The skin can then, if the flow is hard enough, can then tear away, etc. So it's kind of the same thing. And so you can imagine how this could result in an undesirable situation, such that the gate valves would not be able to block the flow completely if you close them completely. There's usually a gap. And there's some famous incidences in industry, one at a petroleum plant in Texas, where catalyst material was continuously cycled to a reactor and back to a holding tank, and one of the gate valves was left partially closed, so not a lot of it was exposed, not a lot of the gate, and it's like a steel flat plate, and the flat plate got eroded, and there was issues with the process where they needed to stop the process by isolating the reactor. Unfortunately, the gate valves that closed did not close completely. Some of the catalyst material, the catalyst was actually used to block the vapors from coming through, but the catalyst just kept on running past the gate valve because there was a leak. And eventually the fumes, there was a pressure drop, fumes started to go backwards through the process, and eventually it ended up in an electrostatic precipitator in the presence of air, and with the electrostatic discharge, it blew up the plant. It was really bad. So it's very important to design valves correctly and also operate them correctly. So that is what we are going to go on about currently. Now, a typical control valve uses a plug that sits on a seat. There are some other variations depending on what is required by the process, but this is the kind of go-to. Now, a gasket is usually present at the seat to ensure that when the plug is fully plunged towards the seat, a tight seal can form, stopping the flow completely. And obviously these gaskets and these seals can be worn out over time, and so you obviously would need to replace them. A typical control valve can be operated pneumatically. If you go to the distillation column, the glass column in our labs, you will see a pneumatically operated control valve where there's a large disc that is covered up, but you will be able to see that. Usually in lab you get to actually operate it, so you are more orientated with the process. Now, typically compressed air is used to activate the valve pneumatically. Note, however, that during a loss in pneumatic pressure, the control valve can be designed to fail either in its fully open position or its fully closed position, and this will depend on the process and what is required to ensure safety during events like power outages or when something goes wrong. Sometimes you want a valve to fail open so that a tank behind it doesn't completely flood, spilling all the liquor all over the place. Sometimes you want it to fail shut because you don't want any more reagent going to a reactor doing a reaction that then cannot be controlled safely. Now, in the image shown on the left hand side, the actuator forces the plunger closer to the seat, and as such this valve would fail in the fully open position when the force acting on the actuator is lost due to something like a loss in pneumatic pressure. A control valve can have many different configurations of plugs and can also achieve the particular requirements of that process as such. So if you have two streams that are flowing together and you want to open the one or close the other, etc., you can also do this using a double port. So this can be various types of single port control valves as shown on top, or you can go with the double ported control valves as shown in the bottom of the slide. In the design of piping systems, a distinction is usually made between the normal flow rate, a maximum flow rate, and the design flow rate. The normal flow rate is what is being planned for the process when it reaches 100% of its operation capacity. So if you are designing a new system or new plant, you will design it for so many tons per annum. This is called the normal design flow rate. Now, some processes might require that the flow rate increase to some maximum flow for very short intervals only, and this is also considered when you are dealing with fluid movers, and it must be noted that the normal flow rate is still typically used in the case when designing a pipe line, etc. But there are different factors that we use, which we'll get into now. A good example is when I was working on a batch process where wood chips are fed into a digester, about 300 ton, and you have a liquor that is generated after you have passed steam through the wood chips in order to start to degrade them. What you would then do is push up neutralization liquor, which would be at a certain flow rate, just to neutralize the liquor that has formed inside the digester, and then once the digestion is complete, then you would reach a maximum flow rate out of the digester as you're discharging the contents. So this is a good example of managing different flow rates, a normal flow rate that is generally expected and one that exceeds this normal flow rate in only short intervals where you have 10,000 liters per minute leaving the digester, so that you can discharge it quickly, and therefore you can then fill the digester up again quickly and limit the time between batches. Now, control valves must always be able to control the flow even at the normal flow rate, and this is intuitive but often overlooked. So therefore the design flow rate is what is chosen in such a way that the control valve will not be in the fully open position at normal operating flow rate, so that it can still control even when you have reached your normal flow rate that is for the process at 100% capacity. Usually the design flow rates are about 5% larger than the normal flow rate to ensure that the control valve is not in the fully open position and still can achieve the control that is required. Now, the following design flow rates are typically used when designing things like batch processes, normal or typical processes, and special processes, where the maximum expected flow rate would be significantly larger than the normal flow rate, but obviously the maximum is not something that you would operate at continuously for a very long time. Okay, so there's a distinction between a normal flow rate, which is what you would expect for 300 days of the year, with very small changes in this flow rate. In the design of control valves, two approaches are typically taken, and these are based on handling non-flashing liquids or gases and vapors. So depending on whether you have a liquid or a gas or vapor, you would go with a different approach. So for non-flashing liquids, this design equation shown here is typically used, where the CCV refers to the control valve coefficient, which is found in literature or in the Appendix H of the handbook. If you turn to this appendix, you will see that the coefficient specified is for certain types of nominal diameters. So obviously, if you're dealing with a 80 nominal millimeter diameter pipe, you would try to match the control valve with that pipeline. Now, be sure to make a selection based on whether you're dealing with a double port or a single port type valve setup. The delta PCV is just the pressure drop that exists across the control valve. However, this is in units of PSI. So just be careful of the units when you're dealing with this equation. X refers to the valve position and takes on a value between 0 and 1, while f of x is the characteristic flow area of the valve that is dependent on the actual construction and operation of a valve, as well as the type of valve that we are dealing with. Now, in dealing with gases and vapors, a relatively large pressure drop can be expected across the control valve. The criterion for compressibility across the valve is that the pressure drop across the valve should be greater than 10% of the upstream pressure entering the valve. So this is a similar criterion that was used in chapter 5, if you remember. There are two main equations that we typically use with compressible flows, namely the average densities method and the Massanellian equation. In the average density method, the fluid traveling through the control valve is going to be polytropic, and we approximate it as being isothermal for the calculations that we will be doing. The following equation is used for this and appears on page 92 of the handbook. Typically, you would want to do a trial and error kind of iteration, but this obviously is not ideal for us. Even if you have a computer, it can be quite difficult to do. For more accurate computations, the trial and error method would be required, but Masonalen derived the following equation, which actually avoids this for us, which is quite nice. It shows, it should be noted that that these design equations, both for the liquids and for gases and vapors, make use of the design flow rate and not the normal flow rate. So just remember this, unless you are then doing a check later, but we will get into the actual design procedure. So typically when using these equations, we first use them at the design flow rate, and then we check our design at the normal flow rate. So remember, we design control valves so that they are still able to control at the normal flow rate, and so the design flow rate must be used initially in these calculations when we are introducing them to the mechanical energy balance, but we'll get into this now. Let us now quickly turn our attention to the characteristics that can be expected from various types of valves that are used in the control philosophy. Although the most typical control valve would be the plug type, other types may also be required depending on the process in question. So, for example, that previous example I gave of a batch digester that's filling up, you would funnel in to the top of that digester the wood chips, and you would use a butterfly valve which can open quite easily against the wood chips that are sitting on top of it. So this would then obviously be the preferred type of valve to be using for that situation, a solid that needs to pass through the valve, rather than a plug valve, because the plug can be quite a small entrance, and the plug itself can also get in the way of the flow. But this is, all these choices really has to do more with the process dynamics and control philosophy that you want to follow, where the type of valve characteristic is chosen in such a way that the process control can be achieved efficiently. For quick opening valves, the response of the actuator or to the actuator in the beginning is quite fast for low values of X, as shown here. A linear trim type valve is typically used when linear pressure drops are required across the valve. In this case, a linear relationship exists between the control variable and such. So, for example, the control variable could be a composition or a reaction rate, and the flow of the manipulated variable can be things like the temperature or the pressure, for example. Now, equal percentage characteristics are more sensitive to movement when the valve is closer to its fully open position. This is typically used when a pressure drop across the control valve is not constant. Ball valves would typically have this type of characteristic, while globe valves tend to be more closely linear, as shown. A butterfly valve is another example that I've now used of a type of control valve that is for certain types of applications, but not for all. It is best achieved when the valve or the control is best achieved when the valve is already in the fully open position. As you can see, as you start closing it from the fully open position, the response in this case will be quite good. Here I show some more examples that you can study further, so you can pause the video and then just take a look or take a note of the design and how the different types of actions between the open and closed positions affects the response of the valve. Now the following diagram shows the pump curve, which is plotted together with the system curve. The system curve is a graphical representation of the mechanical energy balance, which we were first introduced to in chapter 3, equation 3.20, and we also dealt with it more in chapter 4 when we went on to look at the Darcy-Weisbach equation. Note that at zero flow rate, the system curve reduces to the static pressures of the end point and elevation pressures. With increasing flow rate, pressure drops due to friction, and differences in kinetic energy alter the system curve upwards as shown. The difference obtained is the contribution by these variables, the subtotal variables, and is referred to as the subtotal variables as such. Right. So you can now put this more into context. The red point shown on the curve is the operation point of the system, and this represents the maximum designed flow rate that can be achieved by the system when the control valve is in its fully open position at the normal design flow rate. It depends if you are using this for the normal or the design flow rate. Okay, so you can obviously get a different system curve as such. As the control valve closes to restrict the flow, the operation point moves down the system curve according to what is required. This is achieved by adding the mechanical energy balance to this additional pressure drop across the control valve, as shown by the red arrows. Now, if we have a look, what type of control valve could be selected if the process is being operated at the following areas indicated in the green regions? If the desired flow rate falls within the following region, then a linear trim characteristic is typically going to be used. If instead the design flow rate falls within the yellow region, an equal percentage trim is instead going to be preferred. And what of the last region? Can you think of the type of characteristic which could be used instead? In the design of control valves, a few rules of thumb are typically applied. The following applies only to systems with a fluid mover. I will pause here just for minutes to remind us that these rules must be used with some common sense and educational decisions. Okay, so do not just apply these rules blindly without thinking first about them, or you may make a mistake in doing so. So firstly, for the optimal economic design, it goes without saying that the control valve position should always be less than or equal to 1 at the designed flow rate, since a control valve cannot be more than fully open when operating at the normal flow rate. It is just physically impossible. Try to open your tap at home when it is already fully open, and then close it again quickly before someone sees what you are doing, if you haven't managed to jam it up somehow. And also just be careful of water hammer. Don't close it too quickly. However, a valve should also not be allowed to have too much control over the system either, and so it should never be allowed to operate in the position that is too close to being fully closed, which is what Rule 1N stipulates for the normal flow rates. Okay, so you can kind of see where we are getting to. We are going to apply these rules shortly in a procedure, but just keep in mind that these are rules of thumb. The first two rules are obviously limitations which should always be adhered to. The next two sets of rules are more general, and remember, these rules are summarized in the textbook for you, so go over them yourself and just read through their descriptions and make sure that you understand. Now, these two rules say that the pressure drop achieved across the control valve should be balanced and moderate. It should not be too much or too little. It should just be right. So in other words, the pressure drop across a control valve should represent approximately 25% to 50% of the subtotal variable pressure drops. So that refers to frictional drops in pressure and the associated kinetic energy drops. At the design flow rate, this should lie between 50 and 150% of the normal flow rate. Again, just remember that these rules should always be used loosely. So just apply them loosely based on your best engineering judgment. It may be that a rule, for instance, will not hold, but you should also know that you should try different designs, but you should also just not use these rules as is blindly. Just remember to think about it and make a call that is a good compromise if in any event it comes to this, where rule 2n doesn't really fit, but rule 2d is good. Okay, so you just have to get a good feel for this. Now, a good way to approach this is just to remember that the economic design should always be achieved, or else such a process would simply not pay off in the end, and will usually override the second batch of rules for this instance. So if there's an issue with the pressure drop considerations, then just make sure that at least the optimal design can be achieved. So what does a design procedure look like exactly? Well, firstly, the valve position is assumed to be fully open at the design flow rate. Okay, so this is what we choose, and then the pressure drop across the control valve at the design flow rate is calculated using the control valve calculation that was previously discussed, depending on whether it's a liquid, a non-flashing liquid, or a gas or vapor. And as a result, we satisfy rule 1D automatically. Okay, so this is achieved automatically. Next, we determine the subtotal variable pressure drops at the normal flow rate, and then we can prorate for these at the design flow rate. Then we can just check the rule 2D is satisfied, and then calculate the pressure delivered for the fluid mover using the mechanical energy balance, and just assume for now that the design and normal pressures that are being delivered by the fluid mover are more or less going to be the same. Then determine the pressure drop obtained across the control valve at the normal flow rate and check that rule 2n holds. Now you can determine the valve fraction of the total area and check that rule 1n is satisfied in the end. If not, then choose a control valve using a different nominal diameter, rinse and repeat. For gases and vapors, you can determine either the upstream or downstream pressures. Remember that there's going to be quite a big pressure drop depending on the system requirements. Okay, and then use the mechanical energy balance again to determine the other variables. Now assume that the valve is going to be operating in its fully open position again at the design flow rate, and check that the other pressure P1 or P2 before or after the valve using the Massenalin equation. Just calculate that, and then check that the rule that is applicable is automatically achieved. Okay, so obviously rule 1D is going to be automatically achieved. Okay, so then next calculate the pressure drop, or the pressure that is being delivered by the fluid mover. Okay, so it's not a drop, it's a delivery by the fluid mover using the mechanical energy balance, and then determine the normal pressure drop that exists across the control valve as such, and then you can check rule 2n will hold. And lastly, as before, calculate f of x using the control valve equation, and then check that rule 1n is satisfied. If not, again, choose a control valve with a smaller nominal diameter, and then this will ensure that you push the you push the pressure drop a little bit up, and then the valve has to be operating slightly more open. Now, when you are designing a flow sheet, care must always be taken as to where the valve is going to be located. This configuration that is shown is often used for obvious reasons, where the alternative would be the following. And realize that in this case, cavitation is more likely, and this will also reduce the net positive suction head that is available for the system. As such, this configuration is usually going to be a bad choice in design unless you can't get away from it. So for example, well, I don't actually have a good example, but if you need to pump a liquid out of a tank for that is, you know, well below the where the pump is located, but you don't want liquid to run out of the suction line of the pump. You want to always make sure that the pump is always primed. Then this configuration would be good, because that would mean that if you close this valve, the liquid would run out of the leg, the pipeline that lies before the control valve, but there's always going to be liquid between the control valve and the pump and the downstream operations. So in that case, you would probably use this configuration, but other than that, it's not always going to be a good design. Now, in the case where a control valve is to be installed in an existing pipeline, the following procedure is typically followed. It's similar to the previous ones. So firstly, you should check that there is sufficient pressure available by calculating the pressure drop available at the design flow rate using the mechanical energy balance, and then check that rule 2D is satisfied at the lower limit. Now, in this case, if it is not, you should of course adjust your design, but if it does, then you can go on and calculate the following terms using the design equation, and then choose a control valve CV that is larger than this term, or these terms together. Then follow this by checking that all the design rules apply as before. Right, and with this we end off the lecture.